I will talk about my master thesis that is based on entity search and the creation of documents that are called virtual documents using graph embeddings.
Just on time.
Hi.
So we had the introduction and I start.
Okay, so I skipped this because already Alessandro explained something about Sease. So starting with me, who I am. I joined Sease in November, so I am R&D search engineer, and I have a master's degree on computer science engineering, and I'm passionate about big data and in particular clustering and these kind of things, and obviously information retrieval. And I'm also an organist and I play in the music academy. So giving a brief overview of the talk, first of all I will spend some words on entity and entity search and the state of the art in this kind of information retrieval. Then the solution I designed for my thesis, and some evaluation in order to see if this implementation brought some improvements or not, and then some conclusion. So starting with the background, entity search is based on entity. Entity is an object that is identifiable in the world. So clearly a person, a place, or for example here an animal, and usually is the thing that we are searching for when we make query, for example in Google. An entity can be represented by some features. In particular, in our field, we can associate to an entity a URI that identifies the entity in a unique way, and it has some attributes such as, for example, a name or the birth date in this example, or the kind of word. So all of that things that represent and are connected to the entity. So entity search is the search that aims to retrieve this kind of entity, and in particular in the thesis we focus on the ad hoc entity search. So we are looking for one specific entity inside the corpus and the collection. So in order to use this kind of entities, we have to represent them in some way, and we use the RDF language in order to do this. So the RDF is based on triples. In particular, a triple is composed by a subject, a predicate, and an object. Here is an example of RDF graph, because all of these triples can be put together forming a graph. For example, here we can see the subject Michael Schumacher at the center of the graph, and then the triple is composed by the node Michael Schumacher and the other nodes that we see around. So for example, Michael Schumacher is the subject, first driver is the predicate that indicate the types of relation, and then the Spanish Grand Prix, for example, that is the object. So we could directly use this kind of triples in our research. For example, using some languages such as SparkQL, but this requires that the user know some features about this kind of representation, in particular how they are stored and in the specific structure. But we would like that the user can make its information need through a natural language in order to achieve the entity that he is searching. So we would like to reconduct our research to a text retrieval type of research. And actually, nowadays in the state of the art, there are two types of methods in order to create documents starting from these RDF triples and then do the text retrieval. And these documents can be created or in a text-based approach or in a fielded one, structured. And in the text-based approach, in particular, we take all the triples of an entity and then we concatenate all the triples in one document, creating one document. While in the structured-based approach, we exploit also the fact that, for example, the triple is composed by the three parts we mentioned before, and so we would like maybe to differentiate the documents in fields and considering this kind of feature of the entity. And the idea of the thesis was to create documents that not rely only on a specific entity, but that consider also the context in which the entity is placed. As we've seen before, an entity is connected to the other through the RDF graph, for example. And so we would like to create a document that contains not only the information of a single one, but also the entity related to that one. So we have to find a way in order to represent the entity, but also the context in which it is placed. So in order to do this, we use graph embeddings. And this is a method that allow us to create useful representation that are numerical vectors. And these numerical vectors represent not only the entity itself, but also the connection with the other one. Graph embeddings is based on neural network, and it is very similar to Word2Vec. In particular, I will explain a little bit Word2Vec, and then I will explain the method I use based on graph, because they are very similar. Word2Vec is based on a neural network that receiving input a word and predict the nearby of the input word. So the words that are more likely to be near the one we give in input to the neural network. And in order to train the neural network to do this, we create some word pairs for the training. And these pairs are based on context of the phrase we are using for the training. So we take one phrase that is, for example, the one I write here, and we consider a context that in this case is constituted by two words. So we consider the first word of the phrase that is, for example, the, and then we look at the context of that word that are the two nearby. So we create the word pairs starting from the context. So we have the cat and the cheese. So we repeat this process for each word of the phrase, creating all the word pairs necessary for the training of the neural network. Word2Vec, not2Vec is based on the same concept. So the unique difference is that instead of using the word, we use the entity that, as we've seen before, is a node of a graph. And the context, for example, as shown here, is the other nodes that are nearby the one we give in input to the neural network. So we can think that it is the same, but instead of using word, we use nodes, and the context is the nodes nearby the one we are considering. So the solution we design is based on this approach for the representation of the entity, that is the first phase of all the pipeline. So we have all these RDF triples that represents our entities, and then we create a useful representation of this entity through novelty, obtaining a set of numerical vectors. And then we use these numerical vectors that are called entity embeddings in order to group them by similarity and to create the documents we say before, because we have said that We want document that contains entity, but not just one, but more than one that are related and highly connected one to the other. So we use the group of entities in order to create the documents for the retrieval. And then the last part is the retrieval on the entities, and I'll explain later. So starting from the entity representation, we took the RDF triples taken from Dbpedia, that is the RDF representation of the Wikipedia pages. In particular, we used the short abstract, that is the first part of the Wikipedia page, and the most important part is the info box, that is the one on the right of the side, on the right side of the page. And this is important because it contains the link to the other pages and other related, in this case, entity, because we associate to a page of a Wikipedian entity. So the connection gives us the graph that we are explained before. So this is an example of the graph we used. In particular, we use only the nodes that represent a page of Wikipedia, that are the one in green. While, for example, there could be other attributes related to the entity that are the one in orange that are not considered in this process. Okay, so as we said before, we use novelty. This is just a list of the parameters that we can set in this phase. So, for example, how many features we want that represents our entity. So, more features we use, and more specific is the representation of the entity, and the context of the graph. So, how many nodes we want, and other parameters like this. So once we have this entity embeddings, we group them using some clustering approaches, in particular one called k-means sort, that is has some good features like scalability and easy to initialize and something like this. And thanks to this phase, we could group the most similar and related entities together. So once we have these groups of entity, we create our virtual documents. And this is just a schema of the creation of the document. In particular, we take one cluster and we consider the entity inside it. And for each entity, we retrieve all the RDF triples that are representing the entity, and we put them in a document. So we associate to a cluster a document. So for one cluster, we have one document containing all the RDF triples of the entity inside the cluster. Then, once we have all these documents, we have to execute the retrieval on that. And we, as we said before, we want to apply the classic text retrieval on this document. So we use for the ranking the BM25 model. And then the last part, that is the one where there were made more different approaches, is the entity retrieval. I call entity retrieval because after the text or information retrieval we have done, we obtain a ranked list of documents, but our documents in this case are a set of entity. But the user that makes the query would like to receive one entity or a list of entity and not a list of group of entity. So we have to extract from these documents the entity and create a new ranked list to give to the user. And in order to do this, there are two different approaches we use. One called combination system and one called fusion system, that use the previous one and also the state-of-the-art that I explained before. So in the combination system, we take the first cluster of the ranked list we obtain, and then we look inside the cluster to the entities that are contained in it, and we execute another ranking of the entity, just the one inside the cluster, and we put them in the final ranked list that we give to the user. And this is repeated for each cluster, so we pass to the next one, we take all the entities inside it, we re-rank them, and then we put in the final round, creating a new list. And this is the basic approach, but there are other 2 or 3 that I implemented that I'm not explaining here, but that are there are small differences from this one. So for example, I don't know, considering also the rank of the cluster from which the entity arrived, or adding some weight to the entity. Well, the fusion system is based on the previous one and in the state-of-the-art one. So we start executing the classic entity search, so using documents that contains just one entity, obtaining a list of entity in this case, and then for each of them, I in particular I select a part of them, looking to their scores. So I just take those entities that have a score major than a threshold, and I insert it in the final run. Then I would like to enrich the run I give to the user, adding the other entities, a part of the other entities that are in the same cluster of the one we are considering. So after taking this entity, I check its rank to decide if to add it or not in the final run. And then I take the ranked list of the entity inside the cluster as before, and we add them in the final run. So there is a mix of the 2 things, because we start from the state of the art, but we add other entities looking to the cluster we create. So some evaluation of these 2 approaches. In particular, we've done 2 different kind of evaluation. One that is quantitative and one qualitative. So in the first one, we just see to the average measure, while in the second one, we look at each single topic and how each method is the performance of each method in that specific topic. So just to give an idea, we can see in green the state of the art for the entity search for the first approach, and we can see that the state of the art in this case is better than the 3 different approaches that we implement. So this is the reason why we decide to implement also the fusion system that consider the state of the art, but also the clustering and the documents we have created through Note2Vec. That is this one. This is the fusion system. And here we can see that, in particular for MAP and DCG, there are one of our approaches of the fusion system that obtains a little better result with respect to the state of the art. Here is just to show the distribution of the AP measure for each topic, so for each query. As we say before, the combination system doesn't work better on state of the art, so we can see that all the query are under the red line that is divided into the space, and so we can see that only, for example, in the topic track entity 9, we obtain better results with respect to the state of the art. While in the fusion system, we can see that we are more near the state of the art as in respect before, and there are a few more topics where we do better than the state of the art. In particular, for example, this one, that is the quiz chefs that have a TV show in full network. We can see that one of our approaches, that is the yellow one, performs better respect to the BM25 of the state-of-the-art, that is the one in green. And this, I look to the documents retrieved by my methods and the one of BM25, and I see that there are many entities that are relevant for the topic that are put in the same cluster of the first one, for example, that is Retrieval from BM25. So the entities we add are actually relevant for the topic that we search for. So just to conclude, the diffusion system use both the approaches, so the state of the art and consider the clustering. And we have seen that there are some problem in performances due to the fact that for the evaluation we use pooling methods that rely on a set of judgments. So we see that some entities that are actually relevant and that we retrieve with our methods are not at all judged, and so they result not relevant with this approach, but instead they are. And there will be a lot of other improvements that there should be done in this process. I also test because I had not had so much time to make some changes, especially in deciding how to create the cluster. So, for example, the parameters we use in the Node2Vec implementation and all the things like this. So there will be a lot of stuff to do, more of this. Oh, thank you. This is all.
Okay, so thank you, Anna. So if you have any question for her, we can make them now, and then we move to the pizza.
So can I just ask something from my understanding? The BM25 state of the art you say, is that without clustering or with clustering?
Without. It depends. The state of the art is without, but we execute the BM25 also in the approach with clustering. So before we use clustering, we create documents, and on that documents we use the classic BM25 that is using the textual information retrieval.
So the baseline that you used, is that the with that?
Is there are two approaches, but both use the BM25, the classic BM25. But that is the model we use for the retrieval.
So the combination branch and the fusion branch, both of them, so one is using clustering, one not, and both of them, the green line was the baseline that was using BM25.
Yeah, because at the end of both we obtain documents, and then we can think a document as we don't know what there is before, just documents. So there we use the classic BM25 and so on. Yeah.
I also have a question. You said you have one cluster per document, so one cluster, one document, right?
Yeah.
What is the cluster made of exactly?
The cluster is a set of RDF triples. So, okay, no specific, a set of entity embeddings.
Okay.
That comes from the
Okay.
RDF triples.
From embedding the triples, okay.
Yeah, so they are actually embeddings.
Okay.
Yeah, because Node2Vec is based on numerical vectors, so we use, yeah.
So with Node2Vec, you kind of lose the predicate from the.
Yeah, we see that there is a problem with Node2Vec because it consider the nearby entities, so you cannot a bit understand which are the entities nearby, but it don't exploit the type of the relation of the node. So he know that that node is connected to this one, but it should be useful also to know which kind of relationships there is between the nodes.
I think people usually do, I think it's called transit, where it's basically like node to vec, but they have a matrix in the middle that is kind of a translation based on the predicate type. So you are learning like this, for each predicate type, you are also learning like a translation of these two vec.
Okay.
Would that help with negative relationships? With let's say negative relationships. I imagine that there might be some relationships that are. Well, I can't come up with an example now, but let's say there's a relationship has worked with, and then there might be a relationship that is. Well, you wouldn't really bet that an example has not worked with.
So I've never really done this for graph embeddings, but I've done it for, let's say, different types of interaction. So imagine that you have, I don't know, two reactions to some content that is like or dislike.
Okay.
So you could have like the model these translations for these two types of relationships, and yes, one can be negative and the other can be positive, but you can also, you could potentially even query it in the sense of, given this entity and this relationship, give me the most similar.
Okay. That's our recommendation.
Yeah, it's very interesting stuff.
Okay. So in that case, the translation is for like, and I mean the two kind of predicates are basically the type of interaction.
Yes, but I think that the original paper is a Google paper by Google. It's called Transit. It's from basically
From graphs.
It's for graphs. So I think it's exactly this use case that you guys have. But it's very similar. Like conceptually, it's like node to vec, but there is this additional.
Yeah, I think also that nowadays there is something that you start to use also the relationships inside the graph, because my supervisor said it last days, but I didn't see. Yeah.
Okay. So thank you, Anna.
Thank
Again.
you.